calculate the correlation coefficient, the formula is the sum of yi times bi over the square root of the sum of yi minus y bar squared times the sum of bi squared, where yi is the ith order sample ascending and bi is the normal score of yi. Y bar is just the sample mean in this scenario. Calculating bi. So this is really the hardest thing that we're going to have to do. So the normal score has two different meanings in statistic. The first is the z, or standard score, and these are values transformed to follow a standard normal distribution where mu equals 0 and sigma equals 1. The second definition is that the z-score of the value from a sample standard normal random variable with the same rank, I ascending. That second very complicated definition is the one that we have to use for Ryan Joyner. So let's break this down a little bit. The z-score of the value from a sample standard normal random variable with the same rank. So let's say we have n equals 30 samples in ascending order, and we assign each an index starting with 0. So the lowest sample would be index I equals 0, and the largest sample would be index I equals 29. Then we transform each of these indexes using a formula, and we calculate the z-score using the inverse of the standard normal distribution. So here is our transformation equation, where I is the index. So we have I plus 1 minus 0.375 over n plus 0.25, where I is the index of the current index, and n is the total number of samples. Then to get bi, we will take the z-score using norm.s.inverse, and it might be different depending on what software you're calculating this in, and then we would just plug in that transformed I to get bi. So let's pop back in and let's start to kind of filter this out a little bit more. We're going to now say that RP is the same, bi equals norm.s.in of I plus 1 minus 0.375 over n plus 0.25, where y again is the ith ordered sample, y bar is the sample mean, and n is the number of samples.